Hello friends, welcome to another tutorial in network analysis and synthesis. We'll talk about composite filters today. Now, having discussed constant K type protocol filters and M derived filters, we'll extrapolate our knowledge to design a composite filter which is going to solve a few problems that even M derived filters could not solve. So I have this journal block diagram of composite filter drawn on the paper, but first of all we'll need to understand why we do it, and after that we'll see how we do this. So the answer to why is that a little bit of recapitulation will help. In M derived filter, for example, if we were to draw the low pass filter designs response for a constant K type filter, it used to be pretty sluggish. So we used to have FC and F infinity pretty far away from each other, which was undesirable. So providing infinite attenuation to stop band was pretty much solved by the M derived filter. So we had sharp cutoff frequencies. So if this was thought of to be the response of M derived filter, this was our K type. So we could achieve this in M derived filters, but the problem of zero attenuation, or as a matter of fact constant low attenuation throughout the pass band, was still not solved. Now please understand, from 0 to FC this bandwidth is pretty large. So within this bandwidth we ideally want our attenuation to be 0. So we do not want the signal to degrade at any point in time. We want all the signal to get passed through from 0 to FC. So please understand, the response of the filter towards the attenuation as we move from 0 to FC is what is addressed in composite filter. We want this to be 0 ideally, or as low as possible, but we do not want it to vary a lot, because we do not wish that the attenuation, if it is pretty low at initial frequencies and it has started to increase as we move up in the range. So this is what we do not desire. We want the constant low attenuation throughout the pass band. So this is what was achieved by composite filters. So if you understand why this is done, so this is done because of this problem here. So zero attenuation or constant low attenuation throughout the pass band was the reason to make a composite filter. Now if you look at the design of a composite filter, it is made up of a constant K filter section. So this part is a constant K filter section, and then we have an M derived filter section, and then we have terminating half sections. Now please understand, in the designing of composite filters, we'll make terminating half sections out of an M derived filter whose M will be 0.6. So this is a super important point. I want you to highlight this point. So this is a super important point. I want you to highlight this point, because you'll need to draw two M derived filters while making a composite filter, you'll need to make one in M derived filter that you would need to put in to the filter section itself. That will have M which will be given, but for the terminating half section you'll have to derive another M derived filter with M is equal to 0.6 all the time. And I do not know the exact reason why it is kept to be 0.6, but the rationale behind using this M is that if you use M is equal to 0.6, it'll keep the variation of attenuation in the passband to be the lowest. There will be no variation of the attenuation. So having said that, let's try and understand how this is made. So what we have is, if we were to draw a composite low pass filter, the question would look something like this. So we need to design a low pass composite filter to operate with the design impedance of 500 ohms, M is equal to 0.2, cutoff frequency is equal to 2000 Hertz. So by using this data, of course, we have K and FC. The step number 1 will be to find out L and C, and then step number 2 will be to draw K type low pass filter, and we'll draw the T section first, and I'll tell you the reason why we use T section for designing a composite filter. Now if you know that by using K and FC we can find out L and C, and then we can draw a low pass filter section for K type filter, then you'll know that in step number 3, by using this M which is given, we'll draw the M derived filter, again a low pass filter, and its T section. And in step number 4 we'll make another M derived filter, again low pass filter, T section, but this time around we'll use M is equal to 0.6. Over here we'll use 0.2, and here we'll use M is equal to 0.6. And the reason is that from this M derived low pass filter will make 2 half sections, and we'll use those half sections to terminate the filter. So if you know these steps now, step number 1, find LLC. Step number 2, draw K type low pass filter T section. Step number 3, draw M derived low pass filter T section with the given M, and step number 4 will be to draw M derived filter section T section with M is equal to 0.6 for 2 half sections. And in order to understand it better, now a constant K type composite filter is made up of a constant K section, so you can place it here, and then you need another M derived section, so you can join it. As in the diagram, you need a constant K prototype low pass filter, then an M derived low pass section. Of course here M will be our 0.2 as mentioned in the question, so it will be given here in the question. We'll find L and C and we'll substitute here. We'll find the values of ML by 2 and all these component values using M is equal to 0.2, and now we'll join these. And joining T sections is far more easier than joining pi sections, and that is the reason why we always prefer making composite filters using T sections. Now we are done with the K type and M derived filters joining. Now the last part is designing. Now please see, we'll design another M derived low pass filter T section, and another advantage of designing a T section is that this time around we'll use m is equal to 0.6 because we'll split this T section into two parts. And how you can split that? You can simply split the components in the shunt arm like this. Now if you use MC by 2 will get MC. So please understand that splitting a T section to form two half sections is pretty easy from an M derived filter. So I hope this point is pretty clear, that because we'll need not fiddle around with these ml by 2 in the series arms. We simply divide these two components into two parts such that their resultant is this. So after having designed another M derived filter with 0.6 M, we can surely find these values, right? Because L and C will be the same, and then we'll split this. I'll tear this apart. So now we have two half sections. So we place one half section here and we place another half section here. So this becomes our final composite filter for this question. Now if you look at the question statement once again, we need to design a low pass composite filter. Now a low pass composite filter, of course the first step is to find L and C from the desired cutoff frequency that we wish and the design impedance K, and the first step will facilitate us to draw this constant K type prototype filter, which is a constituent of a composite filter. Then we'll draw the M derived section, because in the question it is given that M should be 0.2 for sharp cutoffs. So this will help in meeting the objective of sharp cutoffs like this. So it will not have a sluggish response. Now what is finally left is a constant response of attenuation throughout the passband, which is achieved by these two terminating half sections. And I've tried to make it easier to understand as to how you can use T sections to make terminating half sections, and then you can of course combine it. So this remains as it is, this becomes a shunt arm, this remains as it is, this becomes the shunt arm. You can combine these two to add up, and then this becomes a shunt arm, this remains as it is, shunt arm. And so this long two-port network will be your composite filter. And I'm going to find out the values of L, C and the component values using M is equal to 0.2, the component values using M is equal to 0.6, and then I'm going to fill these values into this filter, and my composite filter will be ready to use. It will give me a sharp cutoff at 2000 Hertz, and of course within the range of 0 to 2000 Hertz the attenuation of the filter will be constant and minimal. And I hope this tutorial was of help, and if you liked the content of this video, give it a thumbs up, consider sharing the video. I'll see you in the next video, and in the next video I can perhaps design a high pass composite filter and make it a numerical video without the hassle of making you understand all the interconnections which are there in the composite filters. So I'll see you in the next one. Take care, have a great life ahead. Bye.